And I'm still letting people present.
All right. Well, thank you for having me. In particular, for still wanting for me to be here, even though I couldn't be here at the rest of the conference. And I apologize to all of you whose talks I missed. So what I want to talk about is something that we've been working on for a long time. And basically, the question is very simple. So take some container and I fill it with just dry sand grains, glass beads, something very simple. And I put some things in, I put a little blade in and I rotate it, and maybe I have some other disc and I rotate it, or I shake the thing. And I want to think about what is really the physics that sets the flow pattern that we see. And there's going to be a good reason why I have two objects here. And I'm going to look at the regime of really slow flows, okay? So in faster flows, I think we understand these things quite well, but in slow flows, it's actually pretty unclear what is sort of the physics that's going on there. So let me start with sort of two of the main ingredients that people will tell you that you have to think about. And the first thing is, of course, friction. We think of the simplest, lowest order description of a granular medium is frictional. And what we mean with that is, well, when you take a beaker of sand and you tilt it, I'm just doing, if I don't tilt it enough, right, the material is not flowing, so there is some sort of yield stress. But if I tilt the beaker sufficiently, the thing starts to flow. So let's think about what does that mean for something like a rheological curve. So I want to think about rheology. And so what I want to do is make a plot of the stress, which I will denote with sigma, versus the flow rate or the strain rate, gamma dot. And in rheology, you typically plot it as a function of log gamma dot. That's not so important. And I think the lowest order description that we have is a curve like this. So if you go really fast, if collisions start to play a role, if you come in the sort of kinetic or inertial regimes, the stress goes up with flow rate, as it would be for any sort of ordinary material. But then if we go slower and slower, the simplest thing you can think of is saying, well, friction when you go very slow becomes rate independent, and that's also what you see actually in granular experiments, right? If you take a beaker and you stir it slowly or fastly, essentially the stresses are the same. Now, very quickly you realize that that's not a complete description, because if you imagine that I have like a chute here with grains, and I look at at what angle do the grains start to flow and when do they stop to flow, and where the angle is in some sense a way to control the stresses, you know that these angles are different. You have a starting angle, which is larger than a stopping angle, okay? So, well, a naive way of taking this into account is saying, well, I have, in analogy to friction, I have a starting and a stopping angle. I have now a dynamic friction. So if I'm flowing, I go to this sort of limit. But when I have something stationary, I first have to have a larger stress to sort of make my material flow. And I think this is sort of, it's not unreasonable, but the point is it's really wrong. And so why is it wrong? Suppose that this was the case. Well, I could do the following experiment. I take my chute, and I have sand flowing here. And now I slowly lower the angle. So what I'm doing is I slowly lower the stress. And if I'm on this branch, if I have a branch like this would just simply mean that by adjusting the angle, I can make my granular flow as slow as I want, okay? Well, if you do the experiment, you know that this is not true. It flows, it flows, it flows, bang, it stops, okay? So what we, and I'll show you rheological experiments, what actually happens is that your rheological curve looks like this. So this is something peculiar now. There's going to be a range where actually the stresses here drop if the flow rate goes up. And this gives you an instability, and this gives you this behavior. So that's the first thing I'm going to show you. And the second thing we have to talk about is something like shear banding. So the other thing you learn if you read about slow granular flows is that you make shear bands. And I don't know how well you can see this picture, but this is something I got from the web. This is basically when you Google shear bands. This was an experiment done in Delft a long time ago on a bed of sand, and there are vertical and horizontal stripes on it, and then it was deformed, and then you see that the deformation localizes in very sort of narrow slip planes, and I've highlighted one here in red. And then if you see a picture like this, it's not unreasonable to think that, well, away from these slip faces, the material is essentially a solid. Okay, and very similarly, if you're, let's say you're sitting at the beach and you stir the sand here, nothing happens out there, and it just completely looks like a solid. And the question is if that is true. And I wouldn't be asking the question if I didn't have a sort of contrarian answer to that. So we did some experiments a couple of years ago in the following geometry. And it makes sense to explain this geometry because this sort of split bottom geometry we'll be using all over the talk. So the idea is very simple. You take a bucket, you fill it with sand, and at the bottom of the bucket you have a disc which you can slowly rotate. That's the one that drives the flow. So you see a side view here, you have this disc, and you rotate it, this. And then you can, basically your important parameter is the filling height of your system, and you can look at the flow patterns that you get. Okay, I'm not going to talk about flow patterns here, but one particular thing that you get, if you put a lot of material in, is essentially that the main flow is sort of is localized in a sort of narrow zone here. So what I can do, I take my bucket, I fill it with a lot of sand, I spin the disc at the bottom, and if you look at the top surface, you don't see any motion. Of course, if you look carefully enough, there still is some motion, but it's incredibly slow, so that a normal lab scale, you don't see anything. But the question is the material then still a solid or not? So what we did, we just put an object there. We've done more serious experiments, but this is the easiest way to do it. And so you put a steel ball there, nothing happens, and then when you start spinning the disc, you immediately liquidize the system. And from that, basically, the other important ingredient that I want to talk about is that whenever there's flow anywhere in the system, it really sort of melts the grains everywhere. Okay, so this is another ingredient. So these are the two things I want to talk about, and hopefully come back at the end of the talk, and I won't give you a definitive answer what sets slow granular flows, but I hope to give you some of the ingredients that definitely need to be there in any sort of consistent description. All right, so I'm going to talk about two experiments. One is where we have this rotating disc in a bucket of sand, but at the same time we can apply vibrations. And we're always going to look at very weak vibrations. So these are vibrations with peak accelerations below 1 g. So that means that by themselves, the vibrations don't make the grains move. Okay, they're just going to move as one block back and forth. It's not like vigorous shaking, it's very gentle shaking. So that's one thing we're going to do. And then we have a rheometer, and we're going to basically probe the rheology of the sand while you're vibrating it. And the other thing we're going to do is to say, well, I have here now, again, one of these split bottom cells, and I stir the thing here, but I'm going to stick a rheometer in to probe the rheology of the sand which is already stirred. Okay, so it's a little bit complicated. Typically we are in a situation where this one is far enough away from the flow that the residual flowing material is very small, so you stir it and you probe it far away, and then you start to see what is the rheology. So these are the two things we're going to look at. Okay. So the first thing I want to show you this non-monotonic flow curve, so the relation between stress and strain rate. So we're going to do a very simple experiment. We have this, we have our split bottom cell. We have this bottom disc sitting here, and through a complicated way, it's coupled to our rheometer. I don't want to talk about the details, and I could vibrate this system, and I will do that later in the talk, but not now. But just look at the case without any shaking. So the simplest possible case. Take a bucket of sand, stick a rheometer in, and look at the rheology. And what we're going to do is we're going to control the rotation of the disc. And you see this is very slow flows. This is a rotation every 1,000 seconds. This is roughly a rotation every day, so it's really, really, really slow flow. And then we're going to measure the torques that we need to do this. When we do that, you find a curve like this. And I already scaled out sort of the dynamic yielding torque here. But the precise numbers are not so interesting, I think, in any case. And what you see is that precisely in this range, when omega goes up, so when the rate goes up, the stresses go down. And it's not a very big effect, right? If I would, for instance, if I plot this on a log scale, you barely see this. So you have to look carefully, but it's there. And it is an important consequence, and it's maybe the easiest way for me to understand it is by an analogy. So suppose you're pushing a car, And suppose this car has a really strange mechanical response. So if I push it harder, it goes slower, and if I push it less, it will go faster. Okay, so this will immediately lead to an instability, right? If you just trip a little bit, this thing will just race away, and you will push less hard, and it will just shoot off. And it means that in this regime, I can perfectly well get there if I control the flow rate, but if I just control the stress, as I'm doing when I sort of control the slope of let's say, a plane on which you have sand, this whole regime is unstable. So actually what happens is that only the part where the slope becomes positive again, that's sort of the stable part. These are the really rapid flows, okay? So that's the first thing that we see. And we've done this now for many different types of materials, and this seems to be true for many materials, not for all of them. Some softer, more plastic-like materials don't have this negative slope, but many other materials have. So let's see also what does this now precisely mean. So if I zoom in on the curve here, I have now the dynamic stress here, and it's clear if my stresses are above that, you know, I have only one part of the flow curve, so I will have steady flows, rapid flows. Okay, so if I'm above that critical stress, everything will flow, and if I'm below the minimum here, well, there is no steady flow rate. So the material will just eventually be stationary. But in between, it's more complicated. Okay? So now to test this, you can do another experiment where now instead of controlling the flow rate of your rheometer, you control the torque. So what I'm doing is I have my container sitting there, I put the rheometer in, and I slowly ramp up the torque. So I start pushing harder and harder, and then I see when the thing starts to flow. Okay? So what you get then, so these are typical curves. So everything is plotted now in terms of the torque that you apply. And basically, if you go along this curve and you do that very slowly, at some point the thing just starts to flow. And then there's two cases. So it either starts to flow, but just a little bit, right? I mean, this is a very slow flow over a fairly short time, so that your rheometer just moves a little bit and it gets stuck again. Or you have cases when the thing just starts to rotate and it just, zip, it starts to flow very rapidly. So you can repeat that experiment many, many times. And all the times, these events where you go back, we call them blue and we call the other ones red, and you put it in a histogram, and then you see that these two features of your flow curve, the minimum and the plateau value, in some sense you see back in the statistics. If you're in this flow regime, you see indeed you never have something like this. You know, once the thing starts to yield, it just goes to steady flow. So if the stress is above your plateau value, you flow. And similarly, if you're below the minimum, well, there's a few cases here, but you know, it's a log scale. So the overwhelming number of events are just like these sort of micro slipping events, but the system is not collectively yielding. There's no steady flow. And in between, you can indeed get a mixed case. You can get both cases. So it really now depends on, you know, sometimes your system runs off and keeps on flowing, and sometimes it's just a micro slip event. But you see that this experiment, which is sort of a yielding experiment, is now intimately connected to the flow curve, and precisely to the fact that you have this negative slope in your flow curve. All right, so now we're going to shake the thing at the same time. Okay, so this was the only part where we do sort of the simplest possible thing, where we just take a container and look at the rheology. Now we're also weakly going to vibrate that system. Yes?
System for very slow. Did you shear a lot?
Yeah, there's always a whole preparation history. We did different things. So typically you do shear it a little bit, and then sometimes you either vibrate it or not before. That doesn't seem to matter very much. I mean, for the flow curve, you don't have that problem, right? You always go to a steady state. For the yielding, of course, you could make it very different. So by stirring it, you try to get as close as possible to something reproducible. Yes. And by the way, this is a good moment. You know, please ask me questions, because well, not now, then later. So now we're going to shake the thing. So I'm going to show you now precisely the same graph with this flow curve, but now there's going to be 10 flow curves, right? So, and here they are. So let me get you through this, because this is, it's a little bit dense. So here on top we have the flow curve for no vibration strength, and sort of these curves are for increasing vibration strength. Now gamma is the non-dimensional vibration strength parameter, and so that means gamma equals to 1. That means your peak acceleration is equal to g. So around gamma is 1, you start to just fluidize the system by shaking it. But if you're at gamma is 0.4 and you just only shake the thing, you don't see anything going on. Okay? And now you can look at the flow curves. And, you know, there's striking differences here. So first of all, if I was not shaking, this thing really seems to go to a plateau. And of course, I don't know what happens here because the experiments at some point would take a lifetime, right? But you see, for any finite value of gamma, these guys seem to be going down, okay? And it becomes more pronounced here. So, again, I don't know what happens if I go down another 4 decades there. And it's going to be extremely hard to probe that. But I think the simple picture that I will get out of this is that these things go down. They may go to some sort of plateau value, maybe. But again, the simplest thing is just to assume that they just essentially go to 0. So if you just shake the system a little bit, and you're willing to wait for a long time, any amount of stress will make your material flow. So you get rid of the yield stress straight away, right? Any level of sort of agitations of your system do that. So that's one important thing. And the other thing, maybe let's go back, is that now all these curves, initially I had a curve which just was flat and was going down. But all the curves now basically have up, down, up, until you go to very large shaking strength. Okay? So that's an interesting flow curve where you go up, down, up. And people sort of familiar with rheology know already what's going to come. So this means you have all sort of hysteresis in your system. So let's take one of these flow curves. So this is now zooming in the flow curve for gamma is 0.5. So let's say medium strength vibrations. So this is the stress as function of the flow rate. And here this is basically, it's precisely the same curve, but I flipped it around. And the experiment I want to do now is, instead of controlling the flow rate, I want to control the stress. Okay? And if your curve is non-monotonic, you could imagine that this has a big effect, and this is precisely what you see. So the red curves tell you what happens. So if I'm ramping up the stress, at some point, you jump to the other branch. And if you go back, at some point, you jump down. And maybe surprisingly, the hysteresis loop is not always sort of at the end of your curve, but it's always within that area. Okay? So this now tells you the following. If I do now the experiment with my inclined plane, and I would vibrate it at the same time, which is very difficult for me to do, so you just have to imagine this. Then there's going to be, there's going to be a range at small angles. It's going to be very slow flows, right? And then I increase the angle, and I go to faster flows. And when I go back, there's still hysteresis when I sort of jump back to the slower flow case. Okay, so that's sort of the general scenario. If you now take the limit that you don't shake, so this is the normal way of doing things, well, then the transition is not between slow and fast flow, but it's between no flow and fast flow. And this is actually, this is not easy to study. It's much better to just shake it a little bit. And, for people familiar with glasses, it's better, to do something at a finite temperature. If you do things precisely at 0 temperature, at 0 agitation, everything becomes very complicated. But it's sort of the same scenario here. Okay? And if you want to put that into sort of a diagram, well, you can do it 2 ways. You can think about controlling the shaking strength and the flow rate, and you basically have a slow flow and an inertial flow regime. And in between, you have this regime where you have the negative slope. But since you control the flow rate, you can still access that part. But if you do it differently, if you control the torque and you control the amount of agitations, well, I still have the slow and the fast flow. In between, I have this hysteretic regime, so the system is bistable. It can be either fast or slow. And the only part where you have no flow is now this part on the curve where you don't shake the thing, right? Any amount of shaking will liquidize it. Okay. So that was about the shaking part. Now we can also fluidize the system by stirring it. So now we go to the other experiment. So this is now the experiment where we just have this disc that we drive by a motor, and we stick this blade or this vane into the sand and have a rheometer to look at the rheology. And of course, the first thing you should do is just do an experiment where the rotation rate omega, so the spinning rate of the disc, is 0. So again, sort of simple granular experiment. And what you find, okay, so you have a yield stress. Thing is 0, 0, 0, 0, 0, bang, jumps up. Okay? But now if you stir the thing at the same time, it's completely different again. And I should also say that sort of in parallel, well, Olivier also did experiments like this, but then in a Couette experiment, but the idea is very much the same. You stir the system and then you measure the rheology somewhere else. And so what you see here, these are now different curves for different driving rates omega, and they all have sort of a shape like this. And as is often the case here, if I rescale, you know, the rotation rate of my probe by the driving rate of my disk, all the curves essentially fall on top of each other. And it's a little bit hard to see now if there's a yield stress or not, right? Is this thing 0 or not? So what you can do is just plot it on a log scale. You first have to take the modulus. And what you see is that there's essentially no yield stress. This is sort of an exponential curve, and this is another exponential curve. And again, there is no threshold, right? So once you start, now I agitate my system by having flow somewhere in the system and probing further away what the rheology is. And again, I immediately get rid of the yield stress. So even for very small stresses, the system is flowing, okay? So we've seen it now in two different contexts, and I think it's very generally true. What is also interesting is that basically you have a straight line on a Lin log plot, which means that the flow rate is exponential in the stresses. And if you think about it, on the previous rheological curves that was on a log scale and had straight lines there, that's the same thing as you see here, okay? So, and I don't think we fully understand that, but that is something that rolls out of the experiment. All right. So now I want to make the next point, because let's think about the previous experiment. So I'm stirring the flow somewhere, and I tell you, okay, so if I look further out in the material where there's almost no flow, right, I get a certain rheology there. I lose the yield stress. But of course, when I say there's almost no flow, you should immediately think, okay, so there is some flow there. So is it actually, you know, is it the local residual flow that I have in my system that sets the rheology, that sets the viscosity of your system, or not? So you can ask yourself, if I stir this thing, I can now measure everywhere in the system. I can measure the flow rate, and I can compare it to sort of the viscosity that I measure in that part of the system, and I can see if they coincide. So that's the idea, okay? So what we do here is we do the same experiment. We fill the container up to a certain height, and this is sort of the height that we use, and then we have the probe sitting in here, and we basically measure how the residual flow, so the torsional flow in the system, varies as function of the z coordinate. And sort of near the bottom, of course, it essentially goes to 1, and then when you go to the surface, it drops, and now depending on the filling height, it drops more and more. So if you fill your system up until this height, this is what I've shown you so far, the residual flow at the surface is 1,000 times slower than the stirring rate of your disk. Now, of course, you're not really interested in how fast the thing is rotating, but you're interested in the gradient, I would say. Right? You want to know what the local flow rate is. So since we can fit these curves really well with something like a stretch exponential thing, we can also take the derivative. So this is the derivative to the fits, and this is the best derivative we could take to the data. And then you see that the local flow rates drop even more, right? So going from the bottom to the surface, I think you have like, well, close to 4 decades there, and for the larger filling height, it's even more. So the local flow rates change enormously. And so now the question is, if I measure now with my rheometer, or in other experiments measure sort of the viscosity of the sands, will they also vary that much? And the answer is no. So we've done experiments there, both with the vane, but also just with the sinking ball. So you put a ball in and you see how fast it sinks. It's a very simple experiment. And you see that there is a vertical dependence, but actually it's depending on filling height, it may even go up or down. But the most important part is that, for instance, for the red curve here, the local flow rate definitely changes over more than 3 decades, while the viscosity changes over a factor of 2 or 3. Okay, so this is I think a key point. If I stir the sand in one location and I go further out and I probe the rheology there, I really need to know what was happening further out. In some sense, it's a non-local thing. The local flow rate that I have there is not sufficient to understand what's going on in the sand. Okay? So you can think of this as either as something non-local, which always sounds a little bit mysterious, or you can say, well, there's really another field that's important there, and the physical way I think about it is this is the amount of jiggling of the grains. By stirring the sand in one position, there's jiggling here, and there's still a little bit of jiggling out there. Okay, and the amount of jiggling here is set by the flow there, not by the flow here. So that amount of jiggling is important for understanding the rheology. Okay? So then the last thing, and that is completely new, there's another ingredient there, and that's anisotropy. And well, it's easy to see if you go to these flow curves, but let me take some time to get you through it again. So what we've been doing, we're stirring the sand by spinning this disc at the bottom. And then we probe the rheology with this vein moving either with or against sort of the main flow direction. And of course we know there's all sort of evidence that the fabric of the granular material becomes anisotropic when you shear it. For instance, when you reverse the shear direction, there's usually all sort of interesting things happening. But you can also see that in these sort of rheological curves. So what we're doing here, sort of omega has a certain direction, which we call positive. And then when the torque is also positive, we sort of move, our vein moves in the same direction as the flow direction moves. And I get a certain slope here. If I don't put any torque, I mean the disc is of course still a little bit moving, and this is sort of going in the counter direction. And what you see is that if you move with the flow, the slope here is lower, and that means that for a certain amount of torque you get less flow. So the material really resists that flow direction. And I think that's the intuition we have. If you stir the sand, it builds up an anisotropy that resists flow. So if I'm trying to push it more in that direction, that's tougher than when I try to go in the opposite direction. So here we can do that. We can sort of have a main flow stirring it in one direction, but do the rheology in the opposite direction. And you see that actually the system is much weaker. So this is a more subtle effect, but it's well, it's subtle in the sense that you have to do, you know, a more subtle experiment to see it, but the difference in slope here is pretty large. So this is certainly also an ingredient I think that ultimately we want to be able to model. Now the final thing I want to show you is some experiments where we try to directly probe that anisotropy. So here we see the anisotropy just by probing the rheology. But you can ask yourself, can I do some sort of experiment where essentially when I give you my container with grains, with its shearing history, can you probe the anisotropy in a direct way? And the idea is you can, but it's a bit complicated. So let me take a minute to explain this. So now we go back to the experiment where we can shake. And let me first tell you what the simple idea is. I just have been shearing this thing, then I try to freeze its state. So everything is stationary, but the anisotropy is still there. And then I weakly start to shake it. And the idea is if there's an anisotropy in the system, and I shake it, I start to relax that anisotropy. So the vein that I have there, that probes sort of the system, will start to relax, right? And it will start to sort of relax back. And so that's what we do in the experiment. And it's a bit complicated. Turns out to really do that well. So what we first do is control the rotation rate of this thing and the shaking strength. So that's preparing the system. Okay, and while you're preparing the system, you know, there's a certain stress that you see, and of course the angle. So that's the angle of this disc just increases linearly with time because you're rotating it at constant speed. Okay, so then what I'll do two things at the same time. I switch to a control where I control the torque and control the shaking strength, but then very quickly drop the shaking strength to 0. So now I have the system still under stress, but I'm not shaking it anymore. And since these stresses that I'm looking at are always low, the system is also not flowing, so it just freezes, but it's still sort of under sort of a holding a torque. Then I relax the torque. Now you see a little bit of oscillation. This is purely an experimental artifact because your rheometer and your disc are not directly coupled. There's a little flexure there because you want to do vibrations. Just an experimental annoyance. But now I'm in the situation that my disc is sort of stuck in the sand, and the sand still has sort of the history of the stirring that you did before. And if you start to shake now, then you see that the angle, so the position of the disc starts to relax. Okay? So you have this complicated protocol. The whole point is you prepare the system in one state, you freeze it, and then you start shaking again to sort of see the anisotropy. Okay, so you can do that, of course, varying all your parameters, and I don't want to go into all the bloody details there, but what you typically get is if you follow this relaxation, you get a curve like this, which is sort of logarithmic, but it doesn't cut off here, so you can do a reasonable fit here. And just to characterize these curves, we just look at sort of the initial slope. So basically, we say sort of initially, how fast is my disk starting to rotate as a measure of the initial anisotropy in the system. And then we can repeat that experiment for many different shaking strengths. So these are the colors. And initial flow rates. So this is the preparation flow rate. Okay? And already what you see from this, if you were stirring the system fast, they all sort of go to the same value of the anisotropy. So if you're just stirring the system, at some point the thing becomes anisotropic, and that's it. It doesn't become more anisotropic. But if you stir it very slowly, and in particular if you shake it a lot, the anisotropy is far less. And you can also understand that because the shaking is the thing that relaxes it. So if you just stir very slowly and you shake a lot, you get very little anisotropy. Which, by the way, which is interesting because this is a strategy to have now granular flows without any sort of anisotropic fabric building up, which is very different from the ordinary case. And then one thing which we definitely don't understand, but I can just show you the observation. If I now plot this anisotropy as a function of the stress, basically the curves seem to collapse. So the only thing that apparently the grains care about, they do this whole complicated thing, but it only cares about the amount of stress in my system that tells me how anisotropic I'm going to be. Okay? And this is certainly the sort of thing that I would love to have input and IDs on. Okay, so that brings me to the end. So what I hope to have done is show you that there are three things that I think are necessary if you want to describe slow granular flows. Things that we just see in the experiment and that go beyond sort of a simple frictional description. So the first thing is that all the physics that has to do with yielding, and yielding you typically get when you only stir the system at one position, let's say, is that you have this negative slope in the flow curve. This is sort of the natural way in which at some point the flow really starts to stop in your system. If you just have a simple flat flow curve, you will never get that right. And I've shown you all these hysteretic experiments where you can clearly see that. Now the second important ingredient is that if you have flow anywhere in your system, so this is in some sense the experiment I did, right? I stir it here and then I probe the rheology there. When I flow in the systems, I have these agitations all through my system and I don't have a yield stress anymore. Okay, the yield stress immediately disappears. So any good description of slow granular flow should not only take the stress and the strain rate into account, but also an additional field. And you can do that in various ways. And I think I should advertise the work of Ken Cameron, who's building models like this and actually has been able to describe all the flow patterns that you see in this split bottom cell. So there's a paper, I think like half a year ago in PNAS on that. So there are now descriptions emerging where you do more things. And one thing I think that no one has really tried to model, but we think is an important effect, is that you get also anisotropies in the flow. And I've shown you that we can manipulate these things, and that in some cases they are small, in some cases they are big, and I think they are sort of the next thing to look at. Thank you.
Do you have ever recorded information about dilatancy in this kind of rotation and sharing?
Not we have looked at it a little bit, but it's not a very big effect. So we could never measure anything really accurately. So we gave up. But there's an important question with all of this. I mean, we asked ourselves, well, is it really anisotropy? Is it not just like dilatancy? Because there's an obvious other field that plays a role. I think the answer is the anisotropy. But it's also true that density plays a role, of course. Typically, in steady state, you just go to some sort of density, and then it seems to be less important. But it is really difficult to get an accurate number. But that's a very good point. That's probably an additional field that you also need.
For your first part of your talk,
Yeah.
what are the initial numbers that you're looking at, and how does it compare to what others have, the range that others have looked at before?
It's precisely it precisely goes up when the inertial number becomes of order 0.2, 0.3. So this is precisely the reason that the flow curve goes up is sort of the normal.
But so is there a contradiction between the set of data that were before of mu of I and so on and what you show now?
No. It's just we look at that very slow flow range. That's precisely.
Smaller inertial.
Yes. So the whole point is that we are that whole negative slope that's in the part where basically inertial effects are sort of gone, and the I parameter is 10 to the minus 2 to 10 to the minus 6 or 7. So that's the part where normally you plot just this curve and it goes like this, and everything is in that small region. Right.
So you're saying that there's a characteristic inertial number where you have a minimum, like 10
Exactly.
93 or something like
Exactly.
that. Do you have any idea of what
No.
fixes this number?
No, so we have done an enormous amount of experiments because if you look at these flow curves, there is at least one and maybe there's even two characteristic kinks there. And sort of the very lowest kink we sort of understand because this has to do indeed with sort of the relaxation time that you get from shaking. So if you compare that relaxation time to your strain rate, you get another dimensionless number. But that's not really where that crossover is, and I don't have a good answer to that.
Maybe system size? Or a growing extent?
We've also looked at filling height. It does a little bit, but it's not really. That's not the essence.
We can talk about later. Well, grab 1 and then 2 and then 3, and that's probably it. So, yeah.
So on the flow part, okay, probably this will highlight my misunderstanding of your talk, but is this the same or at least akin to when you have a low reference number, you have a perturbation,
Yeah.
and you have this flow, and that is very long. You have in the case that's 1 over r,
Right.
And if you have stress less, well, r squared and all that, And here, what is the decay of that flow? I mean, you have an idea. You have
Of the flow rate or of the fluidity?
the fluidity.
The fluidity, there the decay seems to be very slow. So this is one of the, so people have seen these sort of effects also, for instance, in emulsion flows.
Right.
And then the decay length is only a few particle diameters typically. Here it seems to be much more direct. But it may also be dependent on the geometry. I don't know precisely, also in Olivier, in your case with the Couette cell, what is your characteristic length? That's the order of grain diameter. Yeah. So here it seems to be a bit more, but it's very difficult to say, that's why we did all these different curves. We also saw that all sort of other things matter, and sometimes even the fluidity goes up, and sometimes it goes down. So it's tricky. We don't understand that.
Forgive me, I don't think I understood the argument of anisotropy.
Yeah.
If there is shear stress, there
Yeah.
has to be normal stress differences. So as anisotropy is kind of necessary. The only way not to have anisotropy is either to have zero friction or to have a hydrostatic fluid.
Of course. What we're saying is that stress, of course, is there. But now, if I freeze the geometry and now I take the stress off, there's still an anisotropy in the system. That's the one that we're probing. That's precisely what we do in the experiment. So that's why we first keep it, relax it, Okay? So of course the stress anisotropy is there.
Yeah, the negative slope has been seen by many people, including Michel, in kinetic-based models. And there the interpretation has been that if you get a negative slope, there's something wrong with the model. Okay. But I think
It's a different range also, right?
it's a different range,
Yeah.
but still they get it with a relatively small number of parameters.
Yeah.
And models similar to that might be useful for.
Let me just be contrarian. I don't believe that. I think this is just a friction effect. If you just go to the friction literature, many materials, if you just do dry friction, also have this negative slope. So what I think we see is an effect here of the friction of the materials, and that's also why I think the type of grains you're using make a difference. So the type of grains where we got the least negative slope was sort of plastic particles. And if you look at sort of friction curves for that, those are the ones that also have the least negative slope there. So I think it's really details of the friction that we normally don't want to think about, but they're actually crucial here for the yielding behavior. That's my claim. And we can fight over that.
Okay, thank you very much.
Thank you.